In this module, we're going to take a look at ARP packet structures, which are really unique because they have no IP header, there's no UDP header or TCP header. We can't filter ARP traffic based on UDP or TCP port values because there aren't those headers. In addition, because it doesn't have an IP header, ARP traffic is non-routable, so it's only for local network communications. I've opened up a trace file called arp-bootup, and I'm looking at packet number 6, which is a normal ARP query. In this packet, we have a user at 10.64.0.164 who's making a query to find the MAC address of the device at 10.64.0.1. I'll click on packet number 6 and we'll take a look at the packet structure. In the Ethernet header, the type field value will be 0806 for ARP traffic. If it were an IP packet, if it had an IP header coming up next, this value would be 0800. I'll click on the ARP portion of the packet, right mouse click, and expand the subtrees. It's a very simple packet structure. First of all, we have the hardware type that indicates that this is an Ethernet frame. Then we have the protocol type, which indicates that this is going to be an IP packet. This is an IP version 4 packet. It's got a 0800 in there. The hardware size and the protocol size should match the hardware type and the protocol type. For example, we know that an Ethernet address is 6 bytes long, and we know that an IP version 4 address is 4 bytes long. There are 4 opcodes seen in ARP traffic. We have an opcode 1, which is an ARP request, an opcode 2, which is an ARP reply, and then we've got RARP, which is reverse ARP. Whereas ARP is used to find the hardware address that goes with an IP address, RARP is used to find the IP address that goes with a MAC address, a hardware address. Opcode 3 would be a RARP request, and opcode 4 would be a RARP reply. But on most networks, you won't see RARP in place. The next thing we have is the sender's MAC address. This is the device that sent this ARP packet. There's the hardware address of the device, and there is the IP address of the device. Now, this is an ARP lookup. It's a request. We're trying to find out the MAC address that goes with this IP address, the target IP address. The target IP address is 10.64.0.1, and we don't know the MAC address. So in an opcode 1, a request, we always fill that field out with all zeros. Let's look at the reply packet. In the reply packet in this trace, it is packet number 7. We can see in the ARP header we have still Ethernet, and the protocol type is IP. The hardware and protocol values are the same as before. But now we have an opcode 2, which indicates this is an ARP reply packet. In this packet, now we can see that the sender is the hardware address 00803E4B3ECE, and this is the IP address of the sender. So we're getting a reply from 10.64.0.1, and that device is giving us its hardware address. The target, the destination for this ARP information, is our user at 10.4.0.164. And that's the same MAC address that used to be in the sender MAC field in the last packet that we looked at. Now, ARP traffic is really quite simple. It's always got the same structure. It never changes, it never deviates from that. They're always minimum sized packets, or they should be. If you ever see ARP traffic that's anything bigger than the minimum size packet, then you've got a problem on the network. In the next section, I'll show you how to apply some filters based on ARP traffic. Now I'm going to build a capture filter for ARP traffic. I'll show you how to build a display filter for ARP traffic, and then I'll show you how to build filters based on the fields inside of an ARP packet. First of all, we'll start with a capture filter. I'll click the Capture Options button, and I'll go into the Capture Filters area because by default Wireshark has a filter in there that's set up to not show ARP packets. Now we can get a general idea of the syntax of a capture filter when we look at the filter string on this capture filter. Interestingly, Wireshark recognizes the letters ARP in lowercase and will build the appropriate filter if you just type that in. So I want to make a brand new filter for ARP traffic only. I'll select the No ARP filter and click New. It'll make a new version of that same filter for me. And while I'm highlighting that filter, I'll just change it to ARP, and I'll get rid of the not in front of it. And that's all you need to do. Click OK, and I'll start capturing packets. Now the network I'm on has got tons of ARP traffic on it. So I see lots of packets coming in. I can see the status line down below, the total number of packets. I'll stop capturing, and then I'll show you how to build a display filter based on ARP traffic. This time I'll go back and I'll open up the previous trace file I had called ARP bootup. I don't want to save the previous packets that I captured, so I'll say no. Now in this trace I have some DHCP packets as well as some ARP packets. I only want to keep the ARP packets. The easiest way to do this is just to type in ARP in the filter line and click apply. That's all it takes. If you want to see everything except for the ARP traffic, you can put an exclamation point in front of it and apply that. I'll clear out my filter now. In addition to just applying a simple filter to show us all ARP traffic or to not show us all ARP traffic, we can also filter based on the ARP packet's contents, the individual fields in an ARP packet. Let's say we're only interested in seeing maybe ARP request packets. I'll select an ARP request packet, and there's the opcode field that indicates this is a request. I'll right mouse click, prepare a filter based on the selected value, and you can see how simple it is. ARP.opcode == 0001. I'll apply that filter. Now I'm just looking for ARP queries. If I change that to a 0002 and apply it, I'm only seeing ARP response packets. Now I'd like to show you where you can get the master list of the ARP field values. This is the location where you'll be able to see the master display list values for all of the protocols and applications that Wireshark decodes. On the main Wireshark web page, I'll select Documentation, scroll down. I'll look at the Display Filter Reference area. And here we have an alphabet line that shows up. It's the index of all the different protocols and applications that Wireshark decodes. I'll click A so that I can see all of the different protocols and decodes that start with the letter A. I'm going to scroll down until I get to ARP. And there's ARP. Now a lot of the fields that you will see in here have to do with ATM communications. I'm just looking at standard ARP traffic on an Ethernet network though, so some of these fields won't deal with the traffic that I'm looking at. But there's our ARP destination hardware MAC address field. And there's our protocol address field. We also have our hardware type. And we have the ARP opcode. That's the field that we just used for the last filter. And as I scroll down, I can see the ARP source hardware type. That's the 6-byte MAC address. And that's about it. I can also build a more complex filter where I could say I'm looking for ARP packets that are not to the broadcast address. And then I should be able to see ARP reply packets or any strange ARP request packets that don't go to the broadcast address. Normal behavior in ARP would be to send a packet out to the broadcast address when you're making a request, a query. So I'll set up a filter to say I want to look for any request packets. So I'll right mouse click, prepare a filter based on the selected value. And what I'm interested in are packets that do not go to the broadcast address. So as the second half of my filter, I'll right mouse click, prepare the filter, and say and not selected. Now my filter says that the packets have to match both sides. It's got the and operand in the center. So it's got to match both sides. It's got to be an ARP opcode of 1, which is a request, and it cannot have a destination address of FFFFF. Now this doesn't say source or destination in it, but we should really never have a source address of broadcast. I'll apply this, and hopefully nothing will show up, and there nothing did show up, which is a good sign. Remember, if you build a filter you really like, don't forget to keep it in your filter set. So this is an ARP request, but it is not to broadcast. I'll select New, and now that new filter will show up on top. I'll say OK. ARP is pretty simple. There are very few filters that you'll probably build on ARP communications, but they're very easy to do. And the nice thing is that Wireshark just recognizes the protocol name of ARP. This trace is really nice because it does show normal ARP communications. And there are two basic communications that you'll see when you tap into your network. The first one would be a gratuitous ARP, and that's what we see when a workstation boots up. For example, in this trace, I have a workstation that's inside of its DHCP lease time. So it sends out a DHCP request packet to the broadcast address. It gets a DHCP ACK back from the DHCP server saying, yes, okay, you're within your lease time. You can keep that IP address. But just because it says that doesn't mean that the client's just allowed to start using that IP address. The client must always do a gratuitous ARP. Now, most of the time you'll see with TCP/IP stacks out there, you'll see them doing 3 of these gratuitous ARP communications with approximately a 1-second delay between each one. A gratuitous ARP packet looks a little strange inside of it, but it is normal and it makes sense what it's trying to do. First of all, the client has been given the IP address of 10.64.0.164. Inside of the gratuitous ARP packet, the client says, this is my MAC address, and I'm 10.64.0.164. Who else out there, unknown target MAC address, has 10.64.0.164? And the client's got to check and see if anybody else on the network has the same IP address before it's allowed to use that IP address. Now, the time column setting that I'm using is the time from the end of one packet to the end of the next packet. That's my typical setting that I use in Wireshark, the seconds since the previous packet. Now I can see the time between this ARP, gratuitous ARP packet and packet number 3 and the next gratuitous ARP packet. It's almost 1 second. The client is just waiting to see if anyone answers back. If they get an answer back, it means that somebody else is using that IP address. They can't use it. We wait 1 more second and then we see another gratuitous ARP packet coming out. Now the client's got to wait at least 1 more second before it's allowed to use the stack. Now at this point we have a 5-second delay, and that could be because the client didn't have anything else that it had pending that it wanted to do. Or it could be because there was some other traffic taking place in the background, some other prep traffic taking place. In this trace, we were only pulling out DHCP and ARP traffic. Now the other type of traffic that's normal would be just a normal ARP query. Now ARP queries normally should go to the broadcast address. We really shouldn't see an ARP request go out to a unicast address. That just has a weird feel to it. So if you go out to a unicast address, that means you already know the MAC address of the target. So you're not doing a normal query. So normal ARP queries will go out to the broadcast address, and a normal ARP response will be a unicast communication. It'll go back directly to the target system. Just as requests go out to broadcast, responses should never go out to broadcast. So that's what we expect to see in normal ARP communications. On some networks, you may also see that proxy ARP is in place. When you see proxy ARP communications, you'll see the workstation doing all sorts of ARP queries, asking for different IP addresses, and every response comes back to give the client the exact same source MAC address. Typically we'll see that in a routed environment where a router just says, look, if you're ARPing for a device on the other side of the router, you're probably misconfigured, and I'm going to go ahead and respond to you. Just send the packet to me and I'll forward it on. So it's really kind of strange when you see proxy ARP style communications. Another type of a communication you might see might be from a device that is doing ARP learning, where it sends out a whole bunch of ARP packets trying to discover who's using what addresses. Now the network that I'm on has a box that is doing ARP learning. So let's start picking up the ARP traffic on this network. I'll click on Show the Capture Options, and I just want to make sure that I have a capture filter already set up for ARP, and I do. I'll click the Start button, and there's all the ARP traffic. So it's this cadent box. And this cadent box up there is sending out all of these ARP broadcasts. We can see the address of the cadent box. It's saying that I want you to tell this address to these other systems, these machines. Here we go. We can see on the right-hand side, it's saying, who has this address? I want you to tell the box that starts with 73.68. Who has a 24.6 address? I want you to tell this box at 24.6. Who has this address? I want you to tell the box at 67.161. So you can see it's looking for multiple network addresses that might be hanging off of this box. And it spews out this stuff all day long, 24 hours a day. It's part of this box's process of ARP-based hacking protection, they say. Basically, in their hacking protection, they are going through the process of proxy ARP. They're setting themselves up for proxy ARP, and then they also do this MAC address learning. So that's another communication that may be normal depending on where you're plugging into a network. Now I'm going to take you through a series of trace files that show unusual ARP traffic, things you really shouldn't see on your network. The first one I'm going to open up is called ARP-bad padding. Now in ARP traffic, you shouldn't be able to read any data in those packets. But here we have an ARP packet, and if we look down into the hex portion here, we can see the word public. And that's sitting in the padding of the frame. So first of all, I'm going to collapse the Ethernet header. Come down here. This is the last field of the ARP structure. Anything that happens after that is padding. But down at the bottom here, in the hex portion, we can see that word public in there, and that's sitting in the padding of the packet. That should never occur. And I'll scroll through this trace file. The second packet does not have anything in the ARP padding. It's all just blank. So this trailer value is showing us what's at the end of the packet after the ARP information. And in the first packet that we looked at, we can take this packet, we can collapse that Ethernet header a bit. Oops, let's go ahead and collapse there. Now the trailer portion, we should not see anything in there. That should be all padded with zeros. And this information was put on by a network interface card that actually takes information out of memory, out of buffer memory, and throws it into the packet to buffer it to make sure that it's the proper size. So I'll go into one of the files, one of the packets that has a good trailer, and I'll right mouse click on this and prepare a filter based on the selected value. Here is the filter. It says eth.trailer ==, and then it's this whole value here. Now I'll apply this to the trace. Now these are all the good packets. These all have just a string of zeros at the end of the ARP data. But what I want to look for is how many packets in here don't have that. So I'll put an exclamation point in front of that filter and hit enter. And all of these packets have something in there other than all zeros. And as I scroll through and you watch this area down the bottom, you'll be able to see something other than zero sitting in those fields. And in some cases we can see words. There's keep alive cookie. Public keeps coming up. We could probably assume that public has something to do with the SNMP system. This is something that has ping in it. 109, 108 meet manager. Oh, I'm going to guess that the SNMP community string, the read community string is public, and the write community string is manager. Gaming, something about gaming. Location, bottom /C, etc. So that's something you should never see in ARP traffic. The next trace file I'm going to open up is called ARP-recon. Now this is somebody trying to learn about who's on the network based on ARP traffic. Now here we can see the padding, the trailer right there. This matches our filter. We're saying we're looking for anything other than all zeros. But look at this padding. That's nice padding because it's just a series of 03030303. And that's what this device is doing. Now it's 0404, 05, 05, 05, 05. So you can see how it does its padding in its traffic. So I'll clear out my filter so we can see all of the traffic. And this is something you just really shouldn't see. This is a device that's going out on the network and trying to find out which IP addresses are in use on this network. Now, unless you know what that device is that's sending these out, you shouldn't see that. Now, it might be something like an SNMP agent that's trying to gather a list of all of the IP addresses of systems on its segment. That might be. But we have the sender's IP address. We know where to go to look for this 10.64.44.20. You'll see that up in the summary window, and you'll see that inside of the packets as well. So at least you know where to go to find out who is doing all of this discovery. This is simple discovery of IP addresses based on ARP. Now, the fact that it skipped a number here, and it doesn't go exactly in order, is interesting. It feels like they've already done a discovery, and they found systems that are up, and they know that 102 is not in use, but they're checking to see if 101 and 103 still are in use. So the fact that it's skipping some numbers indicates that this may have run already. This is not the first time that this discovery process has run. So that's another thing hopefully you won't see on your network. The last trace file I'm going to take you into is one that shows ARP poisoning. This is a man-in-the-middle attack, and in order to perpetrate this attack, we have someone on the network who is poisoning the ARP tables of other systems. The trace file is called ARP-poison. Now there's other traffic in here, but I want to filter on just the ARP traffic. So in the filter window, I'll click ARP and hit return. Now here we can see an ARP packet going out, and it is an ARP response packet. We don't see an ARP query packet in front of this packet. We just see an ARP response packet. We also see something else that looks strange. This is an ARP query, but it's not going to the broadcast address. Typically, ARP queries will go to the broadcast address. Now, to give myself just a little more room in here, I'm going to change my time column settings so that I only go down to milliseconds. I'll select View, Time Display Format, and go down to milliseconds. Yeah, that gives me just a little bit more room. There. Now I can spread this out just a little bit. There. So packet number 3 is a strange one. This is a packet that is an ARP query. Oops, sorry, packet number 5, excuse me, is a strange one. This is an ARP query going out, but it's not going to the broadcast address. In addition, if we look at packets 2 and 3 in that trace, it's strange. Packet number 2 says that 192.168.1.103 is at this hardware address, the one ending in 80. But it also says that 192.168.1.1 is sitting at that same hardware address. Now, we didn't see an ARP query come in ahead of time, so these are unsolicited ARP replies, and that's something that you shouldn't see on a network. That's not normal behavior. After we see the unsolicited replies, then we see a query. And the query says, who has 192.168.1.1? Please tell 103. This is actually a poison checking process. The poisoner is trying to see if they have poisoned the ARP cache of 1.1. So if everything works properly, 1.1 should say, hey, this is my hardware address. But they should send that packet to the poisoner, not to the actual address of 103. And we can see that the poison has been successful, because 1.1 answers and says, hey, this is my hardware address. And he thinks he's responding to 103, and he's responding to the MAC address of the poisoning device. Doing another check, the poisoner says, hey, who's got 1.103? Please tell the other device 1.1. And that device answers back. 103 says, hey, this is where I am. I am at this hardware address, but he sends that packet to the poisoner's address. Then we see some additional communications from the poisoner. The poisoner periodically goes through the process of unsolicited replies. hey, 103 is at my address and 1.1 is at my address. And it periodically goes through the process of checking to see if the communications, if the ARP cache on both devices is poisoned by going out and ARP querying them. So there are a number of things that are strange in this trace. Unsolicited ARP replies and ARP requests going out to a unicast address, not a broadcast address. So those are some of the things that you want to watch for when you're checking for ARP problems on your network.